So this is the second lecture of my Math Will Save the World sequence. And this time it's mathematical modeling in space science, NASA, and planetary defense. I will start with a funny review of the Armageddon movie. Americans have those epic movies, if you remember. One of them was like 1998 with Bruce Willis, and the idea was that the asteroid is approaching the planet, and what they should do, we have like 1 week before everyone die, and the idea was to hire people who will fly very close to the asteroid, land on the asteroid safely, and then have this like rover or this like big machine that will dig inside of it and it lands or dig into it an explosive, then the team will leave safely on time, and then an asteroid will blow up and everyone will be saved. And that was like the brilliant idea of the group. And it worked, obviously, because it's Bruce Willis. He saved the planet for so many times already from many things. So even though it was funny and completely not scientifically correct, it caused lots of questions from the public. What actually we're going to do if something like this will ever happen? Will we just wait for the asteroid to hit the planet, or do we have anything against it? So it was not the reason of what was created after that by the government of America, but it was definitely in the discussions in the public. Do we have any plans? And maybe we should have. Well, it happened, and this amazing office was created. The Planetary Defense Coordination Office was created, and this is the official logo, as you can see. And you would think that maybe they will be also looking into aliens or not, but they were only specializing on objects that are getting too close to planet, and they were trying to figure out what to do about it. So specifically asteroids and comets. It was created in 2016, and they were managing the agency's ongoing mission of finding, tracking, and better understanding asteroids and comets that would pose a potential impact hazard to the planet Earth. This is their official website, and I'll send you the link so you can play with them. Lots of cool stuff happening there, but it has lots of international collaborations as well. Well, there are lots of asteroids. If you never heard about it, but there's an asteroid belt that is full of lots of asteroids. And they are primarily in our solar system, located between the orbits of Mars and Jupiter. So here's the Jupiter orbit, and here's Mars. The Jupiter is massive and has a very big gravity. So it's sorts for these asteroids. It sorts them into distinct groups. And here there are 3 groups: Trojans and Greeks and Hildas. So the green ones are Trojans and Greeks, and Hildas are in orange. And that's how many asteroids we have here. Well, we also need to define what they're talking about when we call them asteroids. It's celestial bodies, usually referred to celestial bodies that exclude large planets and their satellites in the solar system, mainly including dwarf planets, asteroids, minor planets, and comets. Small celestial bodies orbit the sun, but are much smaller in size and mass than large planets. And we have this International Astronomical Union Minor Planet Center that reports how many they found out and observed and classified. So at the current date, they're updating it right now, every day, every month. Right now, they have 1.5 million observed small solar system bodies. So they have, out of those numbers, they have almost 800,000 asteroids. They're called numbered, which means the orbits have been calculated. And almost the same number of unnumbered, 4,500 of comets, and more than 90% of these newly discovered objects were done in the past 20 years because of the technology we have. This is the coolest animation ever. So they're showing all of this massive number of asteroids circling around between Mars and Jupiter. Surprisingly, NASA does not consider the location of those asteroids when they send spacecraft through the belt, because as you know, we did send some spacecraft to travel into the void of the galaxies. So apparently, the asteroids are so small compared to how far apart they are that the odds of striking the asteroid is 1 in 1 billion. That means if NASA launches 1 billion probes, which is not possible, it's too expensive, through the asteroid belt, only one out of all of the 1 billion will be lost due to the collision. So even though it looks so massive and packed, they're actually very tiny and far apart. Well, let's remember the movie Armageddon. So there's so many of them, and some of them might get closer to the planet and pose the danger. So what we're gonna do about it? The idea in the movie was to send something that will safely land, dig the hole, put the explosive, and then people will leave safely, or maybe it will be done by robots. So apparently none of this is happening. It's more also it's so ridiculous that they use this movie now in NASA as part of the training, and they ask hired people or students to detect as many mistakes as they can in the movie to show them how ridiculous it was. But still, what should they do? Because if you know, the agency finds, tracks, and characterize those objects. They call it near-Earth objects. But also, if necessary, they're supposed to mitigate against the impacts of those objects towards Earth. So then what's the solution? I would even ask you to figure out different ideas, but I will spoil it right away. They want to shoot it. Unfortunately, we don't have a cool technology yet to shoot it with lasers, like in Star Wars. That would be pretty cool. And we also cannot guarantee that we shoot it so powerfully that it will destroy the whole asteroid. So the idea was that we don't have to destroy it. We just need to redirect it. And that's when all the cool studies show up about redirection tests. And I will talk about DART. DART test is the double asteroid redirection test. I know a lot about it because, as I mentioned before, our Arizona State University graduate student was hired there, and now she became a very amazing and famous researcher there. So I learned a lot from her. And I'll talk about details of this project in a second. So again, there's so many asteroids. They're circling around, and we're going to talk about math behind it in a second. But as you can see, what they even choose to practice on. So if they decided to shoot something to redirect it, they have to practice it first. It would be nice to choose one, not too far, not too close, that they can predict passing by in a safe distance and to try to redirect it. So so many of those cool asteroids, they're named. Here's the sizes of them. It's actually not always the case that we do have known sizes of those asteroids. So here they are, and so some of them have also complex and odd gravitational orbits around them. So how would you even predict that? And how do you work on that? Probably will be complicated mathematical and numerical research done. Some of them also have interesting old gravitational fields that will have them circling around each other. Some asteroids have a smaller version, which they often call a moon circling around. So actually, that's what they chose. One of the versions of the bigger asteroids, Didymos, and the smaller one, Dimorphos, to work on. And they could predict when they get close enough that they can send a spacecraft towards it and hit the smaller one. That's why it's called an impact, to try to redirect it. And even though there was no danger behind those two, they wanted to do research on it to calculate how successful it's going to be, if it's even possible, and so on. And that's why they call double asteroid redirection test. Mission is the world's first planetary defense test mission, which successfully demonstrated one method of asteroid reflection using a kinetic impact spacecraft. It aims to shift the asteroid's orbit through kinetic impact, specifically by smashing a spacecraft into the smaller member of the binary asteroid system Didymos. So they decide not to approach it closely and shoot with a laser. They just decide to throw a whole spacecraft into it and hope that that will be strong enough to redirect the asteroid. The Didymos asteroid system is composed of the big Didymos asteroid and a small orbiting moonlet Dimorphos, and that's the one they want to hit. So it happened in 2022. DART will, and that means it's already happened, go into the smaller asteroid, a boulder about 160 meters in diameter, and change its orbital period around by at least 10 minutes. They hope it will be 10 minutes, and then I'll tell you how much it was done, because we already know the result. Using ground-based telescope observation prior to and after impact, scientists will be able to compare the previous path to determine how much the orbit has changed. And that will give us lots of information about how successful we were. Launching in 2021, the DART mission is designed to demonstrate a critical planetary defense capability. With less than a year until launch, DART was working together at the Johns Hopkins Applied Physics Lab in Maryland, and they were leading the mission for NASA. So here is an epic video for you. Very cool. So it is indeed as epic as they show it. The research behind it is fascinating. It's complicated. It has lots of cool math behind it. And that's what I like talking about. First of all, here's a size comparison. So they're taking a bus. Here's the spacecraft they plan to destroy by sending it towards the smaller asteroid. And here's a Statue of Liberty and other objects you might recognize. So they take DART spacecraft, shoot it into Dimorphos that is circling about. No, so DART spacecraft will shoot into Dimorphos that is circling about Didymos. That is the size comparison. Again, luckily, none of them were actually a danger for the planet. It was just to practice and see how it goes. And look at how tiny the spacecraft is. So we really hope that this tiny object will redirect this big object. And why the first one is also important, because we will talk about gravity in a second. That is important. This big asteroid make the small one circling around due to gravity. Well, we had a PhD graduate student that graduated from our department, the School of Mathematical Statistical Sciences from Arizona State University, and she got an internship at Los Alamos Lab. And it was so successful, they hired her after this. So she was using math to research asteroids. For example, shock wave propagation through porous solid materials. She started with that. And this was the article about her at ASU, because she did amazing, significant results and was presenting them at national levels at some point. She was modifying existing developed hydrodynamics code to model impact cratering events. She was using Los Alamos Lab's fast supercomputers for complex simulations that showed results in hours rather than weeks. And as a result of this work, she was awarded $50,000 Emerging Ideas Research and Development Grant from the Center for Space and Earth Sciences program. So it was really fascinating to have a graduate student in our school that was doing that while finishing her PhD. By the way, this is what they're talking about when they talk about supercomputers. There are several of them, she told me, And I do keep in touch with her. And that's why I can ask all the questions. So she says some of them work fast, but not precise, and some of them work very precise, but slower for different causes. So if you work in microbiology, which I was talking about last time, then you want to be more precise, and it takes more time to work on cancer cells, genetic mutations, and so on. But with space science, she says, we don't want to wait for weeks. We want to have a faster result and less precise because the space is so vast. So it's interesting that they have to choose which one to use. And luckily, America owns several supercomputers, and many of them are located at the place she's working. So Salamis Lab is extremely famous location. It's in New Mexico. It was designed during the World War II in 1943, and it's a prominent research and development lab of the United States Department of Energy, known for its role in developing the first atomic bomb as part of the Manhattan Project during the Second World War. And now it's continued focus on national security and scientific advancements. So you should definitely read about Manhattan Project. It's pretty scary, but you remember the bombs that the United States dropped in Japan during the Second World War. Well, that was not the first bomb they had. They created the first bomb and tested it in the deserts of New Mexico and Arizona. And that was done secretly by Los Alamos National Lab. And it was so secret that scientists were living on campus with no permission leaving it. So their families were living there for years. They were basically completely isolated. There's like a whole history behind. So when Wendy graduated and became a professional scientist with PhD, she was hired there because she was extremely successful. So there were another article about her saying that mathematician and planetary scientist Dr. Caldwell leads the lab's modeling of the specific asteroid she was working on called Psyche 16, an asteroid that will be visited by a NASA research mission in 2026. So it's pretty soon. Her expertise included modeling impact of explosion craters in rocky and metal targets. So the Psyche 16 is a different asteroid, the one we did not mention yet. She was working on that because they already had some information about it, what it's made of. It was mostly metal, and metal asteroids are interesting because they believe it was supposed to be a planet, but it wasn't developed enough. So she was specializing in research of what happens if you hit it or what it consists of. And they had craters. I actually do have a picture of it. It looks like this. And then they used that research as well for the DART mission. So it was amazing that she was already working on that. And it was the largest M-type asteroid. You don't need to know all of this information, but this is what they knew about, that they had two craters. They knew how deep they are from the observation, and they believed to be different planet core. And they were figuring out what happens if you hit those craters and so on. So what's the complications? Well, this is what they actually modeled to some kind of visualization. The thing is, we don't know what those asteroids are made of. We can try to predict, but we did not visit them to know, are they made of completely metal, 100%? Are they made of sand? Are they made of what kind of, if it's a rock, then what kind of rock it is? As you understand, if you hit a big rock made out of metal, the explosion will not be the same and redirection will not be the same as if you hit something made of sand. So they were trying to simulate different results based on what they know and how serious the explosion is going to be, and will it actually destroy the asteroid, redirect it, or maybe it does nothing. Maybe it's like a mosquito bite, for the asteroid. So this is the equations she shared with me she was using. As you can see, lots of derivatives. It's called differential equations. And they also have partial derivatives, which we kind of mentioned last time a little bit. Those are derivatives with respect to specific variables. You covered in calculus 3 class. And those are famous equations that have to be applied in research like this. And when we ask her what else she's using, she says, most of the thing I'm using is vector calculus, which is calculus 3. A lot of physics. She had to learn lots of physics like orbital mechanics and geophysics as well, because she needed to know what are those objects made of, or at least try to guess. And from there, she was modeling different results from different observations with different guesses of the materials of the impact, let's call it an object that will be hit. So they call it impactor study. Let's go back to the DART mission. So here's the idea. The big Didymos is here, and so the DART mission will utilize the NASA's evolutionary xenon transistor codes or in engines, which provide flexibility in the launch window timing while still maintaining the October 22 impact date at the Didymos system. The smaller one, Didymoon, is circling around. We sending the satellite, the DART mission will launch the object into it and hoping that the hit will be strong enough to change the orbital movement of the Didymoon. And then they will completely record all of this. And of course, lots of observation was done ahead of time. So as scientists, we have to know things. And we were not completely sure what all of those objects are made of. So with passable parameter space for the DART impact, we knew that it was large. It could include different materials, strengths, porosity, topography, and compositions. As you can see, it's not necessarily just a circle. It might have mountains, and there's a difference between hitting a mountain and where hitting the valley, and it would be lucky if you hit the valley, then the hit will be harder and will have different results. Multiple impact codes were used to sample portions of the parameter space. For example, CTH and spheral. CTH is a two-step Eulerian shock physics hydrocode, which is used for shock physics analysis. And that's what they work when it comes to explosions and heating things. The code has the ability to consider multiple materials, and adaptive mesh refinement allows for high resolutions over the areas of interest while maintaining reasonable computational time. And they start defining the parameters. And that's how math is immediately being used in amazing projects like this. And it's kind of cool that in a previous lecture, you heard about microscience and genetics, and now you're listening about macroscience and space science. So they define momentum enhancement factor, momentum of incoming spacecraft, components of escaping ejecta momentum, so things that will fly out after the explosion, flying along the direction of the impact trajectory, and change in velocity of the target. And that's what they're mostly interested in, what will happen with Didymoon after the hit. The change of velocity is delta V. And do you remember what it means to have the derivative of the velocity? It's acceleration. So they want to see what kind of change of the speed will happen after the hit. And that's what they predict, to have a change by 10 minutes at least. Here's some momentum enhancement factors that were defined here. So the momentum of the moon, P, was defined as the mass of the moon by the delta V of the moon, so the change of the velocity. And the mass of the moon is estimated from size of the Didymos, the bigger object. And assumed material properties, delta V of the moon is determined from the period change and the incoming momentum of the spacecraft. So from observations and from scientific knowledge of geodesics and space science, they were already putting in some values for these P's and calculating data. So this is what the Nash modeling is, which means, you see, they have this grid, and just like in old-time coding of the image recognition, they put little dots in the things that they want to track. And that's what they call trackers. So they knew that the basalt will be highly represented in this smaller moon, the moon that they try to hit. And a pressure-dependent plasticity model was designed, and a Johnson-Cook fracture model was there to track damage evolution. So what is happening with those black dots after the hit, and where they're going to go, where they're going to fly. And then you see these different dots being recorded in different locations. So they're called tracers. They were embedded in every cell within the grid in bands across the target. So it's a pretty clever idea to code it in this way. So I'm zooming in it for you. Here you go. Tiny dots here, and then they are starting moving after the explosion. And then we want to see where they're going to go. And also, these trackers will tell us how deep the hole is going to be. So Wendy and her team were practicing different materials, granite, basalt, pumice, and also different porosity. And porosity ended up to be pretty important. So they actually also were trying to figure out what is important: the density, the strength, the size, the velocity. Apparently, porosity was one of the most important features there, which means how porous the object we're trying to hit was. And they were called spherical calculations for the materials with different compositions. They were decreasing porosity for the granite and see the differences. So phi was the porosity, and this is the object. And they also cut it in halves visually for us to see how deep the impact will go. And you see the red dots or the blue dots, that's where the tracers are going to go out. And they will go differently depending on different materials and porosity. So for the second picture, they had 20% porosity, but for the third, it has 40%, and it's immediately changed the result. So it was a range of target properties, was examined to provide best estimates for the impact result, and to investigate how beta varies with target impact properties, impact conditions, and calculations set up. Here you go. So how far those dots were going to go, how deep the impact will go as well. And all of that was different depending on the materials and on the porosity of the object, but also of the angle of the impact. And do we even gonna hit it? What if it's gonna pass by? So don't forget, it's kind of in space, very big differences in sizes. So that also was pretty important. So again, beta was the momentum enhancement factor. And it's pretty fascinating how they started with nothing is happening. And in 3 seconds, we hit. And now there's a difference between no porosity at all. But some porosity means now the hit goes deeper. And these simulations of a basalt sphere impacting into a basalt substrate at a variety of properties shows that porosities will increase, then the beta will decrease, and the crater will become deeper and narrower. So that is also pretty cool. That kind of makes sense that if we're hitting something porous, then the crater will become deeper and narrower, so the explosion will go deeper rather than spread into pieces. So here's the heat map. You see if it's colored like that, we call it heat maps. 20% porosity goes deeper, 45 deeper and narrower, 60 deeper and narrower. No porosity, then it kind of expands the crater rather than goes deeper into it. And here's the formula again. Beta will be bigger if we have bigger. So beta is the momentum enhancement factor, right? If the moon is bigger, but also it will decrease if the spacecraft is bigger, but we don't have enough money to have a massive spacecraft hitting it. So we kind of know what we're already capable of and the sizes of the spacecraft as well. Another interesting thing was to think, what if the porosity will be big or small? So what if it's the target consists of rubble, and they call it rubble piles. It refers to celestial body, typically a small asteroid, composed of numerous pieces of debris loosely bound together by gravity, creating a porous but low-density structure. So basically lots of rocks, a pile of rocks, rather than a porous material, right? So that changed everything as well. Here you go. In green, we did microporosity, which we had before. It was 0 and 20%. But below, they call it macroporosity, which is basically a rubble pile. And as you can see, instead of green color and tiny dots, Now they have lots of big objects and they kind of like rocked piled together, like a rubble pile. The results of the impact is so different depending on that as well. So they also are considering what if it's just consists of a big pile of rocks rather than a porous materials. And they call the difference between microporosity and macroporosity. So all of this was coded using codes and using supercomputers. Here's also different cool explanation that the first picture has zero porosity. So let's assume there's like no pores at all, basal half space. Then it's 20% porosity as before, micropores. And then they decide to figure out 20% porosity, but it will be rubble pile. So it's different. And speed is the same, but the impact was different. And this change of the speed of the asteroid was also different. And the biggest one was if it consists of the big rocks, but then the deeper it would go if it consists of micropores. Pretty cool, rubble piles. This was a successful mission. It went on TV. Wendy, Dr. Caldwell was everywhere on TV, and we published article about her as well. So it was a high velocity impact for NASA's DART mission. The history was made in 2022, September 26, when this mission actually successfully hit the asteroid target, which also was necessarily what they predicted. Wendy told me that in these kind of research studies, even if it passes by and doesn't hit anything, it was still fine. Because by passing by, they would have so much data recorded and used for future research that it was also successful. But it did hit it. It was the first attempt in the world to move an asteroid in space. As a part of the NASA overall planetary defense strategy, DART's mission impact with the asteroid demonstrated a viable mitigation technique for protecting the planet in case we need it, right? So DART targeted the asteroid and hit it, even though there was no poses of threat to Earth. Wendy Caldwell was one of the most important scientists in that lab, working in that group, modular working group, and she finished her PhD at our school. So we're very proud about it in general. And I wanted to show you this.
A very warm welcome to the programme. Now, while most of us were getting some much needed sleep, NASA sent a spacecraft.
That's a BBC, if you can see it. So it was very cool. It was all over the place. We had lots of news about it from all the kind of channels.
Straight into the path of an asteroid travelling at 14,000 miles an hour. It's the first time it's ever been done, and it's hoped that it'll teach us how to change the speed and path of future asteroids and planets. Our science editor, Rebecca Morell, has been taking a look at what happened.
Closing in on the target, images beamed back from 7 million miles away as a NASA spacecraft approaches an asteroid. The details of the rocky world are revealed. But this probe isn't here to study it. Its job is to knock the space rock off course by smashing into it.
Oh, wow.
And this was the reaction from Mission Control. This space rock poses no threat. This is a test to see how we could deal with one on a collision course with the Earth.
I definitely think that, as far as we can tell, our first planetary defense test was a success, and I think we can clap to that, everyone. So, right? So, yeah, well, I think the Earthlings should sleep better. Definitely I will.
Yeah.
And how do you feel? Like, the people working here, we're definitely going to sleep better.
And liftoff of the Falcon 9 and
The mission, called DART, began last year, with the spacecraft starting its epic journey to its destination. The target, a twin asteroid system. A larger space rock called Didymos is orbited by a smaller space rock called Dimorphos that's about 150 metres, that's about 500 feet across. The spacecraft, travelling at 14,000 miles an hour, crashes into Dimorphos, giving the asteroid a kick. This changes its speed by just a fraction, about a millimetre per second. But this is enough to alter its orbit, and scientists can monitor this from Earth to see if it's worked.
DART really is just the start. It's just the first planetary defense test mission. It was spectacular and it's accomplished, and we'll figure out how effective it was. That's really what we're going to learn in the next weeks to come. All right, we hit this asteroid. Now, how effective was that at deflecting it, and what would that mean for using it?
Research could be carried out well in advance. The DART mission is the first step in finding a solution, and in the coming days and weeks, scientists will be assessing whether their test has been successful. It's a demonstration of a technology that could one day save our planet. Rebecca Morrell, BBC News.
So that was so fascinating and so amazing. There are also lots of links. I will send it to you how the progress was made, how they were building the suicidal satellite to hit the rock, and how this is a YouTube video of like 30 seconds of the impact, which we saw in the news. So it's also super fascinating, has lots of math. Did you see how it was supposed to hit the moon, but the moon is rotating, and we sending this satellite from Earth a year ahead, and all of this have to be calculated ahead mathematically. So here's a picture over here, and how it just goes through and hopefully hits the moon. They modeled all of this and made it available for us to play with in 3D. So I was gonna send you this link. I can play with this to see how it's approaching the smaller moon, and you can see where is it, where's the moon, where's the planet Earth. They sign everything so well, it's amazing. And then they show you the impact as well. You can play with speeds, you can play with dates, and you can see the result of all of this from different angles. You see how it spins with time, it counts the dates. And okay, that's a little bit easy. Let's just stop. And they even have like lots of tools here to play with, so we can compare the sizes of the moons with Mercury and so on. But I also really like comparing, let's see. I also like comparing let me show you, compare the size of distance tools. Yes, so pretty cool that you can compare and calculate how far the asteroid is from different planets and objects we know. And they also have lots of settings here to play with, to see the system view, to see, zooms out above the sun. Here you go, and you can again scroll it in time, and then you can follow the target also, and so on. So lots of fun stuff to play with. Here's again. Here is the video of how it's all happening. And I think if I do it, it will show us. Oh, right now it's the real time right now. So that's actually not that interesting. So stories. I think it's here. They explain the mission. That's pretty cool. In general, I'm really happy about all of this 3D modeling and that they made it so available to the public to play with. And here is the moments of impact. Look how it's getting closer. The speeds here are multiplied by 10 of the real speed. I was reading about it. Only at the end, it slows down a little bit to show us like 5 last moments of the right before the impact. So that's also pretty fascinating. You can play and see the sizes and so on, following the target. And they even compare the size of the satellite with other things we already created as human beings. It was so successful that they named asteroids with the names of the 2 researchers, and one of them is Dr. Caldwell. So now we have an asteroid called Wendy Caldwell. That is such a big honor because of how successful all these missions was. So that is also pretty cool, and I will show you in a second.
It's not a threat to Earth because the closest it will ever get.
Here's her personal asteroid now, and she's talking about, that's not Wendy, and Wendy's talking about
was on the screen.
that this asteroid is not dangerous because nobody wants to have a name on a dangerous asteroid and then it'll kill people.
Asteroid is not a threat to Earth because the closest it will ever get to Earth
This
is
is
going to
Wendy.
be a little further away than the sun. Some of the work that I've done has involved cratering on asteroid 16 Psyche, which is the largest metallic asteroid in the main belt. Now, metal asteroids are super cool because we think that they're planets that never fully formed, and also give us some insight into just how much energy it takes to affect a big hunk of metal in space. Now, with the DART mission, we're looking at a rockier asteroid. Now, the purpose of that mission was a test. It was to see, can we change the orbit of a small body in space? So getting the data from that first mission gives us a proof of concept idea of, yes, we can actually do this. And we did. We succeeded admirably. We changed the orbit by a whole 33 minutes.
If you remember, the goal was 10 minutes. So they did it much better than they expected.
I do these models for a team of researchers that work at.
This is Dr. Plasko. And now we have asteroid named after her as well for the success of this research project.
The NNSA labs like I do, and also work at NASA and USGS, and we all come together to establish, okay, what would happen if an asteroid of a particular size and composition hit the Earth? And we also do periodic emergency response drills with FEMA and international disaster agencies so that we know that were something to come at us, we would be able to work together internationally to prevent an impact.
So now those two asteroids named after these amazing women, and Wendy is a mathematician who initially was a pure mathematician proving theorems, but then got into cool geological and physical research of mathematics. They are now in the list of the NASA asteroids ever discovered. Here they are, and official asteroids, and now they have a small bio. It's American research scientist, Dr. Caldwell, at the Los Alamos National Lab. She's a member of the DART investigation team, an expert in numerical models of impact. So again, think about that no matter what you do, you might not know where you end up to. So one of the goals of my talks is to encourage you to attend different lectures, different seminars, and to learn about different things, because that's how she got into this research. As a mathematician that was working in pure math and in biology, she attended some lectures and seminars that were talking about space science, and that's how she got into it. Then she got internship, and she really loved it, and they loved her too, so they hired her as a full-time professional. Just a fascinating idea to think that you will never know where you're going to end up to. So no matter what your major is, just be open-minded and check all different kind of things. So she had to learn a lot of physics fast. And she was already good in coding, so actual physics was and good at math, obviously. So she had to learn about orbital mechanics. And as you can see, it has calculus 3 in it. It has vectors, but also it has some spinning things, which are polar equations, which you're learning as well, and so on. Formulas for the orbital mechanics, and they talk about conic sections, and they talk about polar coordinates, of course, so now you know that. As you can see, there are sines and cosines in the equation, so you need to learn about that. And you are learning about radius, that depends on theta, and the theta is the angular physics, and so on. So they have gravitational parameters, angular momentums, orbital eccentricity, and all of this comes from math and used in physics. So interesting thing, I already showed you this animation that not all movements here are circular. Sometimes they have odd shapes, right? And that also means we need to adjust when we use sines and cosines, right? And this is how it looks in 3D. Also remember that all of this is not standing flat. It moves in 3D. So if you don't know, things in space keep moving somewhere. So we're all traveling basically with like massive speeds. This is how it looks like. It's the sun, planets around the sun. There's the Earth somewhere here and Mars and so on, and it keep moving. And there were proofs about it because of this residue behind. We sent some satellites to go through, and then they recorded this residue, and that's how we even know which direction we're all moving. Well, does it look familiar? Sines and cosines, but in 3D, they're called helix. They create this 3D spiral shapes. And we teach you that in calculus 3 as well, because it's a multivariable calculus, multidimensional calculus. So all of this has cool applications, as you can see. Here it is again, with different angles recorded, phi or theta, whatever you want to call it. And you can also record the heights that were created by those periodic oscillators, periodic movements. If you don't know what it is, but some of you maybe seen this before, that is Fourier transform, which will use Fourier series. And then you guys learn about Taylor series. So all of this is very connected to lots of sines and cosines used together. As you can see, circles with circles with circles with circles are working on tracing different shapes. Because as you remember, we don't really work with exact circles. They're ellipses and they're odd trajectories as well. So we had to be more flexible, trying to learn how to work with these trajectories and orbits. Well, it's called Fourier transform. And that's one of the most useful things you will ever learn. Fourier transform, and there's a fast Fourier transform as well. There's an integral transform that takes a function as an input and outputs another function that describes the extent to which various frequencies are presented in the original functions. So this is the original function. It's not perfect sine or cosine, but we can break it into sines and cosines. And then it gives us the frequencies, which is basically, if you want in simple words to describe it, how high those sines and cosines can go, high and low. This is the Fourier transformation, it's a famous formula. And as you can see, it consists of series that you guys are learning. And it is also used for studying frequencies, angular frequencies, if you put more angles into it and so on. Here's a cool animation from Wikipedia. Someone actually did a really good job explaining that Fourier transform. You can imagine it if you decompose a sound into musical chords, into the sound of a musical chord into the intensities of its pitches. So that's exactly what's happening here. They decomposing it, and now they can say, okay, some pitches were higher than others, some intensities were stronger than others. And that's when we use polynomials. And that reminds you Taylor series approximations, which we just learned. So Taylor series is just the first step that takes you to Fourier series. And as you can see, it consists of lots of sines and cosines, and constants in front of them will tell us how high and low the frequencies will go. Here they are. Look like lots of waves. So, and it goes back and forth. You can go from frequencies back to the original function and so on. Lots of circles. Inside of the circles, sines and cosines. This is called also signal processing. We also use it in imaging processing, image recognition, data compression, noise canceling, and so on. In the next lecture, we'll talk about machine learning, and we use it there a lot in image recognition and noise canceling features. So your noise canceling headphones are using inverse Fourier transform when you listen to your music and you don't want to hear the noise outside of it. Here are the formulas. As you can see, series that collect together sines and cosines multiplied by different constants, but also have different angles. So that is so important and so massively used in different applications. Exponential forms, that's why we teach exponential equations as well. Of course, Kepler's equations are used in orbital studies, and they're calculating orbits. And they also have electric anomalies and electricity. Here's the very not simple Kepler's equations with factorials in it and limits and derivatives and square roots and sines and cosines, and all of this is inside of the series. So that is a solution of such a simple looking equation. What if the asteroid is actually hitting the planet and say it's not very big? Do we want to know if it's going to get destroyed by getting on fire on the way? So there's studies about that too. It's called asteroid comet body. It is going through the Earth's atmosphere. Then we need to know the material ablation, the dissociation of molecules, and the radiation of our planet. And we use famous Navier-Stokes equations for heat-conducting gases. In general, Navier-Stokes equations are used literally in every aspect of the biology and physics. additional equations for the motion and propagation of a friable lumpy dust materials in the air, energy equations, the energy of the translation of molecules, which defines the temperature and pressure, and the combined energy of their rotation, oscillations, electronic excitations, and dissociation and radiation. All of this is also studied through mathematics. The algorithms are used in the combination of the semi-Lagrangian approximations for Lagrange transport derivatives. So I will talk about two most famous things, which are Navier-Stokes equations that describe how velocity, pressure, and temperatures and density are all integrating when we work with the moving fluids and how they're all related. Here they are. The Navier-Stokes equations, they take momentums in 3D or high dimensions, and they also check how it's all related to the energy. And all of those are using partial derivatives, which you learn in Calculus 3 class. And they have velocities and energies and pressure and stress and density. So all of this is also used in space science. Lagrange polynomials are also used, and they used quite often to approximate objects and graphs. So hello, we just learned numerical approximations. We taught you Simpson's rule, and in Calculus 1, we learned approximations with rectangles, but now we also know some other cool ways to approximate things. It's also called interpolation. So they use Lagrangian polynomials, it looks like this, to approximate functions as well. And sometimes it's better than Simpson's rules, for example, or other methods. We also taught you Taylor approximations, which also use polynomials, right, to approximate the function. So it's a choice. Here's the cool animation that shows the comparison of Taylor series, which you guys know about, Lagrange interpolation, Fourier series, which I just mentioned before, Fourier approximations, and Gram projections. The black is the original function, and they're comparing which approximation is better. And not only better, the original function is called 5x sine x all over 1 plus x squared, but also how fast it's gonna do the job. As you remember, Wendy was talking about the idea that in space science, we want things to be done faster rather than waiting for years, while in microscience, we want to be more precise. So it's a choice, and Lagrange approximations are commonly used in space science. They are in blue. In blue, it's getting closer to black, closer to the black line, and then it's getting very good. So Taylor is in green, and you guys learned about that just recently, right? Look at that. Pretty fascinating. There are also things called standard model Lagrangian. It's not the same thing. This model describes all elementary particles and forces observed to date. It doesn't work well with gravity. It's much more challenging to use it near black holes because it has strong gravitational forces. So this is what they use as well, kinetic energy and self-interactions. It's full of functions, and each has meanings and absolute values and lots of cool applications of mathematics again. Finally, I will remind you that the gravity was mentioned, that all of those objects have different gravitational forces. So the sun has a very big gravitational force. The bigger the object, the more gravity it has. And all these have to be included as well. So they're using also relativistic compositions of velocities, which are derivatives. Here they are, and they have transformation of velocities, partial derivatives, as you can see. In fact, when they were sending the satellites, they have to take this into account, that the farther it goes, the less gravitational forces impact it will have on the object we're trying to send towards the asteroid, right? So it will change the trajectory. It's not going to be linear anymore. So that has to be taken into account. And of course, this reminds you something, right? It's called polar equations. See this r cosine theta, in this case it's u cosine theta, u sine theta, and then derivatives of those polar equations. It's not surprising that we use polar equations in space, and a lot of orbital movements are happening, and all of these are also tied with vectors. And we also used centrifugal acceleration that matches the acceleration due to gravity, the classic equations, which you might have seen before. Actually, some of the homeworks you had mentioned it before. But it's also kind of well-known formula in general. Since I mentioned the formula, I will show you how many things we just covered in Calculus 1, Calculus 2 in this lecture. There's like a list of 17 equations that changed the world. And it's like standard, but it's actually really good. So of course we learn in school the Pythagorean theorem, changed the world right away. You will be surprised that the logarithms you think are so silly are super important, specifically the formula that takes the products of two functions and breaks it into sum. That is a very unique property that functions don't usually have. So logarithms takes a product of complicated functions, for example, and break it into something easier, which is a sum of logarithms. Then you learn the definition of derivatives, right? With using the limit. You see this equal sign is here as a mistake. It's not supposed to be here. Then gravitational laws, that's physics. The I squared equals -1. The square root of the -1 is a famous thing done by Euler. Takes you to the complex analysis and complex values, imaginary numbers. We'll skip this, skip normal distribution. That's you will cover that in statistics and probabilities. And wave equations. Those are second order partial derivatives happening in partial differential equation class. Fourier transform, I just mentioned it to you. So Taylor series are taking you to Fourier series really fast. And Fourier series are the one that's used the most. I just mentioned the famous Navier-Stokes equations. They are used everywhere. In those signs, you will learn them in Calculus 3 called gradients. So partial derivatives, gradients, and so on. That's number 10. Maxwell's equations, you probably heard about or not. Check them out online. It's very interesting to learn about them. Second law of thermodynamics. Relativity, of course, E equals mc squared by Einstein. Schrödinger equations are extremely popular too. And then, of course, if you go to space science and you see later years, they start talking about chaos theory and black holes equations. So all of this using lots of partial derivatives, which are basically derivatives, but in upper dimensions, series, of course, logarithmic functions, sines and cosines. And you use all of this mathematics to do an amazing projects like DART mission. So I highly, again, encourage you to go to any possible talks and seminars and online videos you can find, but it's much better to go to real talks where you can ask questions and make connections and try to get hired into this amazing project. So as you can see, working for space, you need to know lots of things. If you're a mathematician, you had to learn how to code, and you had to learn how to work with physics suddenly and astrophysics, geological properties of asteroids. But then if you're a computer scientist, you need to learn more math and physics. And then if you're a physicist, you need to learn more math and coding. So of course, you're not the only person in the lab. Obviously, there was a lab full of engineers, people, computer scientists, mathematicians, mathematical modelers, data scientists, and they had access to supercomputers. And then when they model all of this theoretically, the experimentalists took their research, went to the deserts of New Mexico, and actually blew up a couple of things to check if it matches the theoretical research, and they blew up different things with different materials using all those calculations, which is very fascinating. There's so many cool things happening in the middle of the desert and right close to us here. And I also want to mention that Arizona State University is having strong collaborations with NASA because we all located very close to each other. Arizona, New Mexico, and then NASA is located in Texas, Houston. So Los Alamos lab is located in New Mexico. So all of this has a fascinating collaboration with Arizona State University. And so we are very proud that our own graduate students become part of this project.